Welcome back. This is lecture 9 of the course called Climate Science: A Discussion for Everyone. And we left off in lecture 8 talking about things we might be worried about. And this is a continuation of things we might be worried about. In particular, it's a discussion going to be a little bit of a wrap up of where we were, and then a discussion of a discussion of tipping points. So let me get you set up here, and we'll explain tipping points in just a second. So the idea is we have been talking about, after a little bit of framing of how we do prediction, we talked then about things that we believe will surely happen. And I have this list that you may remember. We talked a bit about every one of these on the list. And when I say surely happen, a lot of these things to some degree are already happening. And so that builds confidence. And plus, while they're each complicated systems of lots of different variables, there is some very good statistics and science behind thinking that these are things that will happen. If you read the book Climate Casino by William Nordhaus that I recommended in the introduction, he says a lot in there that we should distinguish between managed processes that have risks and unmanaged processes. For example, he sorts, now there's a bit of opinion how you sort processes into these different categories, but he would sort, for example, agriculture as a managed process, and extreme weather events or sea level rise as an unmanaged process. The distinction is useful, I think, because in agriculture we would hope that given our technology, we could adjust somewhat to changes. But overall, whether the process is managed or unmanaged, is the point we made earlier, earlier in lecture 8. A lot of this depends on how quickly it happens. So even when you get down to natural systems like coral reefs, there's some chance that some adjustment could be made, some adaptation, even a physical evolutionary type adaptation could be made, can be made with time if the change is not terribly quick. But then, there is this question of how fast it will happen and how much temperature change makes a difference to the result, right? So that's the situation we're in. Now, even if we can adapt, there is plenty of reason to believe that such adaptation will cause changes in people's lives and will cost money and significant movement around the surface of the earth. One of the things people worry about is the migration of people to different places. If you think about sea level rise, think about a country like Bangladesh, which is not very far above sea level, a few feet on average, still has a huge population of people who are relatively, I won't say impoverished, but a lot of them are. And if they started moving, the question is, what kind of problems would we run into? Now, these are all scenarios that are difficult to get your hands around in terms of when and how much and all that kind of thing, because there's just no simple way to estimate those things. But today's section, we want to talk about tipping points and major risks. And this is, I think, an important topic. Again, if you look at Nordhaus's book, The Climate Casino, he almost says, yes, we might be able to adapt to a lot of things, but what we're really trying to do when we set a temperature limit at 2 degrees centigrade, a temperature goal of keeping keeping the warming under 2 degrees centigrade. What we're really trying to do is we're trying to stay away from these things called tipping points. Now, I think this is an important enough subject that I keep poking around with it. I think this topic, I could spend a lot more time here than I'm going to. But a lot of the research on this is just emerging. A lot of it is, in my mind, still pretty speculative, but important for scientists to explore. Right. So we're going to step into this. We all know that physical systems, especially complicated physical systems, have relationships among state variables that sometimes result in a boundary where suddenly the system goes from one point where it's kind of bouncing around somewhat safely, I guess, or in some system, and then you reach a place where it switches to a totally different system, totally different place where it operates. So this is an attempt to give you a conceptual understanding of this. Here's 2 state variables. Of course, the climate system has many state variables, but the little circle there is meant to represent the state of the system as it is. And it is in a kind of equilibrium valley, you could call it a place of operation. And you notice that that it is, I've drawn the arrows through this little ball-like object to show that it's varying more to the right than it is to the left. But what would you hope, what I've drawn is kind of a very broad, flat area where this ball is sort of trapped until its variability or state variable 2 changes enough to move it up towards the tipping point. But you realize once you get to the tipping point, if you go over the edge of this cliff, you're going into a whole different state with a much lower value for state variable 1. And the natural variability, the left and right motion of the little ball, is not going to climb back up that hill into the original equilibrium position very easily, right? So this is something people worry about, is are we approaching, through some variation of state variables, are we approaching a place where the climate system switches? Now you might say, tell me a little more about a physical system that does something like that. And I included here the phase diagram for water. I don't know the extent to which a lot of people have studied phase diagrams for years, but you may not have heard of these recently. So this is for the water, just plain water, pressure on one axis, the vertical axis, and temperature on the horizontal axis. And you can see that as you vary temperature and pressure, the water goes into different phases, different combinations of phases. And there are points like the triple point, the critical point, and other points where you suddenly switch from one phase to another, or from one combination of phases to another combination of phases. So this is the kind of thing that I think people are fairly familiar with. Phase changes, you know, when you reach the boiling point of water, obviously you get a change, pretty dramatic change happening all at once, right? Where you now have water and vapor in a combination. So if you think about, this is a figure I took from Nature, where it's actually a comment article about tipping points, and I just took it because it has some indications, some kind of give you some feeling for what some of the things people have tried to investigate are. So you have a list here of influences on the Amazon rainforest, reductions in area of the Arctic sea ice, possible slowdown of the Atlantic circulation. The Atlantic circulation we've talked about in terms of the Gulf Stream. Fires and pests changing the boreal forests. We said a little bit about beetles, pine bark beetles in the Rocky Mountains in northern Canada. Coral reefs, large-scale die-offs of the coral reefs, ice loss of Greenland, ice loss in West Antarctica, both accelerating, and permafrost thawing, and as well as East Antarctica ice loss. So you kind of have two parts of Antarctica that are melting. Now, some might argue that each of those is a rather large effect on the climate that could bring about increased a change in temperature and other things, or change in sea level, both pretty dramatic. And they could be connected. That is, when some of these things happen, they reinforce the others. And this is part of the thing. This is part of the study, is, how much of that is happening. So I've listed ones that I've looked into a little bit. And I called these bad stuff that's hard to rule out, just from the idea that I don't think scientists are trying to scare you here. They're basically investigating things that could be a big issue if we're not careful. And I will just go through these a little bit to let you to say a few words, and then we have some more data on each of these that I want to show. But let me give you the headlines first. As you may know, the permafrost has a lot of trapped, decayed organic material. A lot of that material was trapped without having decayed in an oxygen-rich environment. So a lot of it has potential for releasing methane, which is a much stronger greenhouse gas than CO2, at least for the first 20 or 30 years of its life in the atmosphere. As the permafrost melts, some of this methane could be released. And so I have some data about that coming up. I think I have waved my hands at before the fact that our ice models, ice melt models particularly, of glaciers are probably crude today. That is, we are seeing or beginning to understand other mechanisms for the way glaciers are melting on land, both in Western Antarctica, and we have some satellite measurements that I'll talk about summarizing later. But this all suggests that our simple measurement of sea level rise that we use, which says, for the last 20, 30 years, it's been 3 millimeters per year. And we see a little acceleration possibly in the altimeter data from satellites more recently of maybe something like 0.08 millimeters per year. But that is based on an empirical study of what we see happening today. But then if you go look at these big areas of ice like Greenland and Antarctica, you begin to see ice melting in ways that suggests that those measurements are not the end of the story. That is, we could be seeing an acceleration in the acceleration, so that 0.08 could be growing pretty fast, and there may well be a tipping point for ice melt, which would drive sea level rise up a lot faster than we expect. We have all heard that the equatorial rainforests are important carbon storage areas. When you burn them or tear them down, whatever the carbon is released, both the carbon in the soil and the carbon in the biomass can be released into the atmosphere. That would be a rather large increase for CO2 equivalent. There is some evidence of disruption of the Gulf Stream, probably due to Arctic Greenland melt. I talked about the thermohaline circulation and how the sinking in the North Atlantic is important to driving that circulation and bringing the warm Gulf Stream up to the northern hemisphere as that circulation proceeds around the Earth and through the equator and comes to the surface again and ends up bringing warm water and air to the North Atlantic. So the question is that happening? We have some paleoclimate indications of events of large freshwater influx that caused the Gulf, that we believe caused the Gulf Stream to go through periods where it was, I don't say it's on or off, but it might have slowed down. So the amount of CO2 that goes into the atmosphere, as we've referred to in the past, is called the air fraction. So we emit a certain amount of CO2, but some of it is absorbed by the land and some of it is absorbed by the oceans. And the percentage of it, of the original emissions that goes into the atmosphere, is this thing called the air fraction. That air fraction could be increasing if the oceans or the land are less able to absorb CO2. And there are various reasons why we would expect that might be true. So I have some slide later that talks about the details of one study that's been done. And then, of course, there is some evidence that we are seeing, actually considerable evidence, that we are seeing large-scale changes in weather patterns. For example, we've had, the breakout of the polar vortex. You probably heard on the news a couple times in the winter, especially if you live up north. And there are some reasons why that might be happening. After all, we said the circulation depends on the movement of energy from the equator to the poles, and we get the three-cell model, and we're probably slowly modifying that by changing the temperature contrast as the northern latitudes heat up faster than the equator. And I have a couple of pictures of that. So this is an aerial map of permafrost regions. These are, the colors represent ground temperatures from something like less than 5 degrees centigrade up to less than 15 degrees centigrade. So that from kind of purple being the coldest, purple being the coldest, purplish being the coldest, down to yellow or orange. The permafrost, it's a very large region, and it's considered to contain probably twice the carbon that is currently in the atmosphere. And as it melts, there might be a proportion of CO2 and methane that would escape, and the exact proportion depends a lot on biochemical processes and what happens in the ground. Some of that's being studied even today. And so this is kind of the way the permafrost is structured. You have a snow cover in the winter anyways. You have a snow cover. You have an active surface, which sometime exposed in the summer months. That active surface has soil decomposition due to plants that pop up in the summer and so on and so forth. And then below that, you have the permafrost, which is actually, sort of from table to base, has got frozen ice and a lot of trapped explants from the active layer before, right? And then, of course, down below that is non-frozen ground as you go down to depth, where temperatures tend to equilibrate above freezing. So if you look at this just as a picture, this picture shows you two things. The first thing it shows you is kind of the structure. You can see here the active layer of current vegetation. And then you go down a little bit, there's kind of a layer here that's frozen, but it's recent vegetation. And then you get down to where it's really ice. You see a lot of ice down here. And you can see that as this layer melts, pieces chunk off. So we have a lot of structural issues. If you go to northern Alaska, indigenous people live in areas where their towns are sinking or breaking apart because of the melting of the permafrost layer that's causing things to collapse and either reduce in you know, kind of sink or break off kind of things that happen. Now, let's switch to the cryosphere. This is data from 2006 to 2015. This is reported in the 2019 Oceans and Cryosphere Report from the IPCC. I mentioned earlier, we've mentioned several times, if you average the last 30 years, you get 3 millimeters per year of global mean sea level rise, with an acceleration perhaps of, you know, almost 1/10 of a millimeter per year, 0.08. But if you look at the amount of gigatons per year coming from various cryosphere contributors like Greenland, Antarctica, and the glaciers, in the 2006 to 2015 range, you get almost 2 millimeters per year. And that is, you know, we expect a millimeter or so of thermal expansion. And so what we're seeing is, in recent times, a shift to ice melting contribution to sea level rise that's even bigger than the thermal expansion. And probably, if we're going to get acceleration, this is where it's going to come from. And what we're seeing in both Greenland and Antarctica is increased melting, increased loss of ice. Now that we have satellites that measure the gravitational effect of the ice in those areas, we can actually measure the ice loss a lot more accurately, even in terms of tons, right? So we get a much better feel for what's going on. Going forward, that's going to help us understand how far off we are in our estimate of sea level rise. Right now, that 2 to 4 feet estimate, more and more scientists are saying that looks conservative compared to what it could be if this ends up being a tipping point where we have a certain kind of melting, but then when you get above a certain temperature, other physical mechanisms come into play. You essentially go into a different state of melting that could accelerate these things rather dramatically. More time will tell with these satellite measurements. This is just an old picture of the 2005 melt extent of Greenland. You recognize Greenland in the middle of the picture here, compared to the 1992 melt extent. So the 1992, this is where melting occurred in 1992, the light pink, and the red has extended that melting further inland on the continent. So you see an increased area of melting. And this has just continued up till 2019. I don't have more recent aerial data, but this is just such a neat picture, I thought we should include it. I want to return to the carbon budget graph, which I discussed earlier, because we're going to switch now to how effective the ocean or the biosphere can be at absorbing carbon emissions that we put in the atmosphere. So you remember that we put in about 50, 22 ends up being the air fraction that stays of the 50. So that's about 44% is the air fraction. 15 gets absorbed by the biosphere, and 13 gets absorbed by the ocean. Now, why might we expect that the ocean can't keep absorbing? Well, as we keep putting it in, the ocean's ability to dissolve CO2, a gas, into the water is less. And so we might expect that and the increased acidity of the water to cause a problem with continuing to absorb. The biosphere is a complicated story. I won't go into it here, but we have a similar kind of phenomenon that as you keep increasing the emissions going into the atmosphere, it's not clear as the carbon dioxide in the atmosphere, as the total ppm goes up, it's not clear the biosphere is going to keep doing it. For a while it does it because CO2 is a fertilizer for plants. So in some sense, plants grow a little more aggressively. But after a while, that effect is saturated. So, and as we said before, the 0.4 is the only way that we're really taking the CO2 out of the carbon cycle and burying it for a very, very long time, right? The biosphere and the ocean are constantly interacting in the carbon cycle. So This is a study that I found in Biogeosciences recently. Well, it's 2014. I think it's been updated a little bit in 2016 or 18. But what it says is that that basically the air fraction in an initial measurement, anyways, seems to have gone up. That means that back in the 1950s or 60s, it would appear that the air fraction was more like 30%. So between the oceans and the biosphere, they were absorbing 70%. Unlike today, where the air fraction is 44%, so the oceans and the biosphere are absorbing less today than they did back then. Now, there's kind of a little bit of good news, a little bit of bad news there. The bad news, of course, is as we keep pumping it in, the air fraction goes up, meaning that we're not being helped as much by the ocean and the biosphere and keeping the temperature down. However, it says if we stopped, maybe as the CO2 concentration dropped, we'd be able to take more out. However, again, the error bars on this are very large, so it's difficult to be sure exactly how much has changed. And so this is an area of concern going forward. It's not at all clear that there's any kind of linear relationship here with concentration in the ocean and how much it can absorb. It could be a tipping point type thing. But future sink effectiveness is probably dependent on emission rate, and it's going to be, we got to get better measurements to really know what's going on here. Now, let's just briefly talk about large-scale circulation patterns. We've talked many times about the three-cell model as a way to think about this. And the basic point I want to make here is that the difference in temperature between the equator and the pole is what drives this model, as we've said several times. And so as the poles warm up faster than the equator, we're beginning to change the engine of energy that sits behind this model. And that may change differently depending on regions of the world you live in. The way the Ferrel cell might be modified by local bodies of water and things like that. To give an example of something that people have pointed at, and I think I showed this slide once before to explain a possible mechanism for why the poles are warming faster. But if you look at this, we're saying that the jet stream depends on the contrast. The strength of the jet stream depends on the contrast between the polar cell and the Ferrel cell. And if that contrast goes down, we would expect the jet stream to be weaker. Now, there is some evidence of this. There are these waves in the jet stream that have been there even when it was strong. They're sometimes called Rossby waves. They're basically a sinusoidal boundary between the cold air and the warmer air. And those waves move at a certain speed around the planet. So when the jet stream is strong, the waves go faster. What happens when those waves occur, depending on their amplitude, they bring cold air down into the temperate zone, into the Ferrel cell, let's say. And of course, warm air gets pushed up into the polar regions. But if the wave moves slower, then you get these cold air, cold air coming down, lasting a long time, like maybe a week, and you get these cold spells that suddenly come across. So then what you get is a climate, as you say, geez, the Ferrel cell is experiencing warmer winters. However, every once in a while, you get these polar vortex incursions, which give you a real dose of cold weather. So you can have a very cold, extreme temperature during a warm winter. And as I might have mentioned before, this is sometimes called climate weirding rather than climate change, W-I-E-R-D-I-N-G, weirding. So in summary, you know, I could say that there have been, you know, this is the kind of thing that I probably should spend more time on and have more details, but it's a lot of speculative work going on the boundary right now of what we understand about this very complicated system. There is no question we're disturbing this system in a significant way relative to changes in the Earth's history. We know that it's a complex system. We know that complex systems do sometimes respond with sudden changes from one physical state to another. A point in time where the system tips over, so to speak, or changes its state. So the ideas above are only some of many possibilities. I saw one study with climate models which discovered some 37 different abrupt changes if you ran climate models into the future with the business as usual for maybe 100 years, the business as usual emissions rate, which I don't think is realistic. I don't think that's going to happen. I think we're going to get wiser than that. I hope we're going to get wiser than that. But one should understand that in that model study, 18 of those 37 large regional tipping point or large regional changes in climate that seem to come very suddenly happened between 1.5 and 2 degrees. So one of the reasons that the Paris goal of staying below 2 degrees was really endorsed was to try and stay away from some of these effects. And there's plenty of evidence, there's beginning evidence that some of these effects are beginning to show up. You know, certainly you can see the permafrost melting. One of the estimates right now is that by 2100, it would add something like 200 or 300 gigatons of CO2 equivalent to the atmosphere if we keep on the same path. And so there's you know, these are things we're beginning to see. And so that's one of the reasons the 2 degrees is important. So we want to say our goal here is to try and reduce risk going forward. To summarize this, what are we worried about? We're saying there are things that we know are happening. If temperature changes slow enough, we might be able to adapt to these things at some cost. The costs are difficult to estimate. There are other things that would be very difficult to adapt to. If they happened, they might be fairly sudden. Fairly sudden doesn't mean a year. Fairly sudden in this time scale means tens of years. But they might be fairly sudden, and they would be add a real difficult problem to what we would do to adjust. And I have only explored some of those. I mean, people would quickly add the continuing acidification of the oceans as an example of something that could be a serious problem that we haven't talked about. So this is the end of lecture 9 on tipping points. Our next lecture is going to be about what can we do about these things. And we'll begin that in lecture 10. Thanks again for taking the time to pay attention. Thank you.